Welcome back, students. We are back with another lesson, lesson 55. In this lesson, we'll discuss mass defect. It has been studied that any stable nuclei, okay, let us suppose this stable nuclei has a mass small m, okay. The mass of this stable nuclei is small m, fine. Now let us consider the mass of this proton. This is mp, and let us consider this one as neutron, mn, fine. So what it has been noticed that the mass of the nuclei is always less than the sum of the mass of the proton and neutron. Okay, actually they should be equal. Why? Because protons and neutrons, they together make up the nucleus, isn't it? But what the researchers have found is that the mass of the nucleus is always less or approximately or very less. Okay, let us say it is very less than the total sum of the mass of the proton and the neutron. Okay, so there is some difference in this mass, isn't it? So the difference between the rest mass of the nucleus and the sum of the rest mass of its constituent nucleons is called as mass defect. Fine. So let us consider this nucleus. This nucleus, let us say this to be any random chemical element X. This element X has how many nucleons? A. The mass number is A, and Z protons, so atomic number is Z. So if it has Z protons and A minus Z neutrons, then the mass defect can be written as delta M. Delta M denotes your mass defect. Then you have, if the mass of an individual proton, let us say, is MP. Okay, now how many protons are there inside the nucleus? Z. So what will be the total mass of all the protons? It will be ZMP. So I've written ZMP. Fine. Now next, let us consider your neutron. If neutron has a mass small mn, okay, this is the mass of an individual nucleon. And how many total nucleons are there? Total nucleons is A minus Z. So the total mass of the total neutrons inside this nucleus will be how much? The mass of individual neutrons times the the total number of neutrons. So this is A minus Z neutrons. So what will be it will be this quantity. So I've written this one. Fine. So inside this, what you have? The total mass, this is the mass of the proton, and this one is the mass of the neutron. Fine. And this m denotes the mass of this nucleus. So the difference between this mass is known as your mass defect. Fine. And this is the expression for your mass defect. So next we'll discuss about binding. So any stable atom, okay, inside any stable atoms you have protons and neutrons. These nucleons are bounded to each other by a very strong force. Okay, they are bounded with each other with a strong force. Now if I want to break this proton and neutron into individual particles, then I have to do some work, isn't it? So the amount of the work done gives us the idea about the energy by which these two nucleons are attracted or bounded to each other. Now that energy is known as your binding energy. So the binding energy of a nucleus may be defined as the energy required to break up a nucleus into its constituent protons and neutrons and to separate them to such a large distance that they may not interact with each other. Fine. So if you have a nucleus of smaller mass, a stable nucleus of smaller mass. Now if you give of this energy, if you give some amount of this energy to break this to break it into individual nucleons, and such that there is no interaction between this individual nucleons. So the amount of the energy which you have supplied is known as your binding energy. Fine. Okay. If your protons and neutrons are bounded to each other, then where is this energy coming from? Okay, this energy is coming from the mass defect which we have studied just now, isn't it? So the mass defect, which is your delta M, we know how much is your delta M. Delta M equals to ZMP plus A minus ZMN minus Mn. ZMP is the mass of the protons, A minus Z number of neutrons times the mass of individual neutrons. So this is the total mass of the neutron and this is the mass of the nucleus. The sum of your protons and neutrons minus the mass of the nucleus gives us the mass defect. So that extra energy is coming from your mass defect. Okay, so from Einstein's energy equivalent mass energy equivalence relation, we can write EB equals to delta mc square. Now in this case, what is your delta M? Delta M is your ZMP plus A minus ZMN minus Mn whole thing c square. So this is your delta EB, which is the binding energy of the nucleus. We know the mass of the proton was 1.007 AMU and the mass of the neutron was 1.008 AMU, almost equivalent to each other. But what about the electron? The electron mass was 0.0005 AMU, isn't it? So whose mass is bigger? The protons and neutrons mass is way bigger than your mass of the nucleons. So sorry, way bigger than the mass of the electrons. So your electrons are very light as compared to your proton or neutron. Fine. So if the mass of the electron is very light, okay, it's very negligible in terms of your proton and neutron. So what do you think? How much energy will it be supplying or it will be contributing to the binding energy? Zero. So the binding energy contribution due to electron is zero. Fine. So if I want to write the binding energy for the electron, by how much energy it is binded towards the nucleus, or by supplying how much energy you can break the bond between the electron and the nucleus is known as the binding energy of the electron. So what will be the mass of the total nucleus? The mass of the total nucleus Mn plus, if this is your electron has what mass, let us say Me. If this is the mass of the electron, now how many electrons will be there? Z. Okay, why Z electrons? Because we know what is Z. Z is the number of protons. Protons means positive charge for stable atom. What should be the charge of an atom? Positive, 0 or negative? 0. If it is 0, that means there must be the same number of electrons in order to neutralize the atom. Therefore, the number of the protons which are inside the atom should be equal to the number of the electrons in order for a neutral and a stable atom. So Z also denotes the number of electrons. So if Z is the number of electrons, what is the total mass of the electrons? ZME. Fine. If this is 1, ZME. So what is the mass of the atom? This should be the total mass of the atom. But what is the actual mass of the atom? Actual mass is the mass which you calculate, okay, or which you get after performing some experiments, okay. That actual mass is this M, mass of the element X, okay. In this case, this one is 0 as compared to the this total energy is 0 as compared to the binding energy of nucleus. That means it is very small. So we have considered this mass defect also very small. If the mass defect is also very small, therefore on simplification I can write the mass of the nucleus as the mass of the element minus the mass of the total electron. Fine. Now we will substitute this one in our equation 2. So in equation 2 we have ZMP A minus Z. Fine. Here you have the mass of the nucleus. And how much is the mass of the nucleus? This one. Substitute this value here. Minus the mass of the element. Minus becomes plus. So you have the mass of the electron. So on further simplification, I can write it like this. Times C square will give us the energy. So this is the binding energy of the nucleus. Fine. Now, let us consider your hydrogen atom. Inside your hydrogen atom, okay, how many protons are there? 1 proton. How many electrons are there? There is 1 electron. Fine. So what will be the mass of this hydrogen atom? The mass of the hydrogen atom will be mass of proton plus mass of electron. So here the mass of proton plus mass of electron should give us the mass of the hydrogen atom. So on further simplification, I can write the binding energy as Z times of mass of the hydrogen plus A minus Z, number of neutrons, times the mass of the neutrons minus the mass of the element times C square. So this is the binding energy expression for any nuclei or nucleus. Fine. We have discussed about the binding energy. That means if these two nucleons are bounded by some energy, then how much energy should be supplied? That energy supplied is known as your binding energy. Fine, we have studied about this one. So if this is your binding energy, then what will be the binding energy of individual nucleons, whether it be a proton or a neutron? So what we have to do to find out the binding energy per nucleon, what we'll do, we will divide it by the number of nucleon. Fine. So the binding energy per nucleon. The binding energy per nucleon is the average energy required to extract one nucleon from the nucleus. It is obtained by dividing the binding energy of nucleus by its mass number. Fine. So if you know it takes how much energy, the energy required is known as your binding energy. So if you want to take only one nucleon, if you want to extract only one nucleon, whether it be a proton or neutron, then you have to supply the amount of that one nucleon only. That amount of one nucleon or per nucleon is known as your binding energy per nucleon. Fine. So how that can be calculated? By calculating the total binding energy of the atom. This is your total binding energy of the atom divided by the number of nucleons. The number of nucleons is denoted by A. A is your mass number. Fine. So the binding energy per nucleon gives a measure of the force which binds the nucleons together inside the nucleus. Fine. So this is your binding energy curve. Okay. So in next class we will discuss some important points regarding to your binding energy of nucleons. Okay. So that's it for today's class. Thank you. And if you have any confusion, please don't hesitate to ask. I will re-explain it to you again. So thank you.